So we're into this last chapter, chapter 15, Sylow theorems. And so the way to think about what's going on here is we, as he says here in the introduction, we remember the Granger's theorem. Granger's theorem is a very early kind of foundational result saying that the size in a finite group, the size of every subgroup divides the order of the group. So that restricts the possible sizes of subgroups. But then that naturally prompts the question, so, okay, that restricts the sizes of the subgroups, but what can you say positively about subgroups, about the existence of subgroups of certain sizes? Okay. So this is the whole idea of having a converse to Lagrange's theorem. And we know that the converse isn't true. A group doesn't have to have a subgroup of a certain size just because that size is a factor of the size of the group. The coursework problem you were working on, coursework's a bit return soon. The coursework problem you were focusing on looked at some of the alternating groups, and through a close examination of them, we were able to find that they didn't have subgroups of certain sizes, half the size. So we'd like to understand, or we'd like to have results that are a bit more powerful, rather than just picking individual groups and doing an extremely close examination of those particular groups and maybe saying, yeah, there's no subgroup of this size, there's no subgroup of that size. And is to get some positive statements out. So the Sylow theorems are positive statements in that they apply to finite groups and they assert the existence of subgroups of certain sizes. And there's three of them, called the first, second, and third Sylow theorems. And the kind of culminates in the third one. Kind of all the results are kind of put together in the third one. Not only does it assert the existence of subgroups of certain sizes, it also describes, the number of them that there are. Okay, so not only does it say subgroups of a certain size exists, it also goes some way to describing how all the possible subgroups of that particular size are related and how many of them there might be. Okay, so just introducing this chapter 15 on Sylow theorems. Have you been keeping up with the recordings? You've been
I've watched the recording as well.
Sorry?
I've watched the recording so far.
Okay, good. So, I've just been making some introductory remarks as he does here about the Sylow theorems, being kind of comparing them to Lagrange's theorem. And the Sylow theorems make positive statements about the existence of subgroups of certain sizes, based only on knowing the size of the group. So it's not like when you're examining the details of the group, particular group detail. Just based on knowing the size of the group, we can, in certain cases, assert that subgroups of a certain size exist. Okay? And it's an application of the ideas of group actions and the class equation. Okay? So we begin, we'll just remind ourselves, and I won't go through, I've given several reminders at the start of lectures about group actions, what the class equation is. So let's just jump straight in and write down the class equation. So G is a finite group. We have this equation which describes the number of elements in G, and it describes it as this object here, which we'll say what that is in a moment, and then these things here. I'll stick the notation he's using is limit to xk. Okay, this is the class equation. This is derived from the action of G on itself by conjugation. So if you take an element little g, then for every x in g, x by sending x to this element gxg inverse. That's the self-action of a group on itself by conjugation. And it's a very interesting, and studying the structure of this action reveals a lot about the group and enables us to prove things like the Sylow theorems. ZG is the center of the group. ZG consists of every element G from the group, such that for every other element X from the group, Gx is equal to Xg. So this is the set of special elements in the group that commute with everything else in the group. It's certainly not empty because the identity element qualifies as an element in the center. And in fact, it's a subgroup. Okay? So this is the center of G. So it's called. Notice this equation here is really talking about the group action by conjugation, because Gx equals Xg, that's equivalent to, another way of saying that is Gxg inverse equals X. Okay? So it's the set of all elements G that act trivially on every other element in the group. Okay. And each element of the center, each element G from the center belongs to a one element orbit of this action. So for such an element G coming from the center, curly O sub G, the orbit, the set of all things that you can move little g around under this action, conjugation, the orbit of elements it travels around is pretty boring. It just consists of G. That's because G commutes with everything else. H and do H, G, H inverse. Because G commutes with everything, you can move the H and H inverse together. It's just the identity. So any other element H, which is acting on this little G by conjugation, you can only ever move G to G. You can't actually move G's. Then the x1 up to xk then are representative. So all those elements which have a singleton orbit, they're all gathered together inside the center. And the other ones, x1 up to xk, these are representatives of the remaining, and by implication non-trivial, orbits of the action. And really, these expressions up here these sums is just the size. These expressions here, are really the sizes of the orbits, but by a theorem in the group action chapter, in chapter 14, we have a theorem that the size of the orbit of an element is equal to the index in G of C of X, where C of X equals it's called the centralizer of the element little x, and it's equal to the stabilizer of x under this action. So in other words, it's the set of every element G from the group such that G acting on X, which is Gx, G inverse, is equal to X. The set of all group elements that stabilize the element X. This is what the centralizer of X is. And again, this is another way of writing that to say that the action under conjugation by G stabilizes X. Another way of writing that is Gx equals Xg. So in other words, it's the set of all group elements that commute with X. Okay? So you get the center of the group, the set of all elements that commute with everything. You've got the centralizer of a particular element X, the set of all elements that commute just with this X. Okay? So the center of the group is contained within all of the centralizers. Okay? Because the groups, the elements in the center commute with everything. Here we're bringing in elements that commute with just this particular X, so that will be perhaps slightly more elements. Okay? And from a theorem from chapter 14, this index of the stabilizer in the group, that's the same thing as the size of the orbit of that element. So this class equation is really just it's just counting the elements of X according to counting them orbit by orbit. And the orbits partition the set of elements G. So, you know, the place where the equation comes from is a kind of a simple idea in some ways, just counting the elements in the set by counting the elements in the different cells, the cells of the partition. Okay, so that's a reminder of what the class equation is. Okay, it takes a few minutes to remind ourselves each time, but I think it's useful just to reinforce these ideas. And since everything swings and turns on analyzing this class equation, it's a good idea to remind ourselves about it each time. Any questions just about that set? Okay. So, another way to think about these things, since we're in the case of G being a finite group, here are also equal to, so this is a group theoretic way of describing this number, the index of the centralizer. Another way to think of it is it's the number of elements in the orbit. But for the case of a finite group, these indexes are just the quotient of the sizes. It's the number of elements in the group divided by the number of elements in the circle. Okay, so it's this nice simple. Of course, Lagrange's theorem tells us the number of elements in the subgroup must divide the number of elements in the group, so it is actually an integer. It's not a non-integer rational number. So that's the case for each of these terms. And it's this, you know, using all these aspects of these numbers here that appear in the class equation, but just analyzing it closely, this is how we prove the results. Okay, so hopefully we'll get to the first Sylow theorem today. But the first result, which is attributed to Cauchy, theorem 15.1, Cauchy's theorem. Well, this is certainly, I mean, it's of the same nature as the Sylow theorems. It's a positive statement that asserts the existence of a subgroup of a certain size. Okay, so the assumptions here is we assume G is a finite group, so it has some size n. P divides n. Do I need to say P is a prime number? We should understand that P is a prime number. Okay, you only ever use P for prime number in these contexts. And then the conclusion is then G contains, so as he's written it in the book, it's G contains a subgroup of order P. Subgroup of order P. Now, groups of order P, think back to some of the earlier work we did with cyclic groups. If a group has order P, a prime number, then it has to be a cyclic. So another way of stating this, just an alternative way of presenting this, is, or you can say G contains elements, an element, but actually more than one, contains elements of order P. Because if it's got a subgroup of order P, that subgroup has to be cyclic, so any non-identity element from the subgroup will generate it. Okay, So all of the non-identity elements in this subgroup, they will all have order P. So these statements are basically saying the same thing. Having a subgroup of order prime or containing elements of that prime order, they're the same statement. Now we've seen something very similar to this before in the chapter on the structure of finite abelian groups. It's essentially the same theorem. It was lemma 13.6. Said let G be a finite abelian group of order n. If P is a prime that divides n, the size of the group, then G contains an element of order P. Or equivalently, G contains a subgroup of order P. Okay. So we've already proved this in the case for abelian groups. So what's significant now, for proving it in chapter 15, is we're not assuming that the group is abelian. Okay. So that's in part. We just kind of glance back at the proof of this, what kind of stuff is being done here. We proved it by induction of the size of the group, and then the kind of significant and the significant part of the induction argument was making use of the construction of quotient groups in order to, and when you quotient out the group by one kind of subgroup, then you'll have a smaller group, so then you'll be able to call on the induction hypothesis, because you'll assume the result is true for that smaller group. And then using the fact it's true for the smaller group, then extending that up back to the original group by using properties of the homomorphism, using properties of the quotient homomorphism. Okay, but now we're in this much harder setting, not the group's not B. Okay, so we can't go changing the order of products, and we can't go assuming that any of the results we previously proved, which were only about okay. But it's still nice to see that you get the very same thing being true in general. Okay. So the proof of this, it's again an induction argument. So induction, we use induction on the order of G. On the order of G. So the base case, well, what's the base case? What's the smallest size of group that you can have the conditions true for? Well, the smallest size of group that you can have this setup is when the size of the group is P itself. Okay. The base case is when G is equal to P. Is there much to prove here? Well, if G is size P, then G certainly has a subgroup of size P, namely just itself. Okay, so again, that's good to see. Like typically the case in induction arguments, the base case is trivial. It's either like just trivial argument or just really an observation. But base case is when the size of G is P, so it's trivially true. Trivially true since G is a subgroup of itself. Or taken the other way, if you take the statement as referring to the existence of elements of certain orders, and if G, again, if G has size P, prime means G is cyclic, and because it's prime order, it'll be generated by any of its non-identity elements. So every non-identity element in this group G has to have order P. They're all going to be generators. Okay, so the base case is true, that's good. So now we assume the theorem is true for all K satisfying, well, okay, so the base case was P. So we're assuming it's true for all K for satisfying P less or equal to K strictly less than this N. Okay, so N is the size of the group we're looking at. But we're assuming that the theorem is true for every group of size strictly smaller than the group we're looking at. So this is a case of strong induction. as these kind of arguments typically are. So we're not just assuming that it's true for k and then going to prove it's true for k plus 1. We have to make use, maybe we have to call upon the truth of the theorem for every group of strictly smaller size than the group we're looking at the moment. Okay. So what we're aiming for now is to prove it's true for groups of size n. Okay, and we want to use the class equation. So we consider the class equation. Class equation for G. So this thing that we introduced at the start. So this is an expression for the number of elements in G, the number of elements in the center, and plus all these indexes of centralizers, and we've one corresponding to each of the non-trivial orbits in the action of G on itself by conjugation. Okay, and the rest of the argument is all based on carefully considering the class equation. So we know P divides this. That's part of the assumptions, that P divides the size of G. So we know this is divisible by P. So then we just look at all these and ask ourselves, are these or are these not divisible by P? Okay. Now it may be that P divides the order of one of these centralizers. For some I. That might be the case. Okay. If that is the case, if so, then that centralizer, that CXI, has order strictly less than n. Because it's one of these centralizer subgroups. It's a small subgroup. Okay. Has order strictly less than n. So the induction hypothesis applies. So by the induction hypothesis, see, it's got size strictly smaller than n, and P divides its size. So therefore, it has, CXI has a subgroup of size P. And that subgroup will also be a subgroup of G. Yeah. Centralizer CXI is a subgroup of G. Here's another subgroup within it, of size P, but that's going to qualify as a subgroup of size P. Has a subgroup of size P, and hence so does G. So the theorem is true in that case. But what if we're unlucky and that's not the case? So that means P does not divide any of the centralizers. If this is not so, i.e., we assume for each I between 1 and k, P does not divide that centralizer. So none of those are divisible by P. But then we make use of the fact, this other way of viewing these terms in the class equation. So recall that the index of one of these centralizers in G, it's a pretty simple enough way to think about that number. It's just the quotient of these two sizes. Okay. Or in other words, that's equivalent to saying the size of G is the product of the size of the centralizer multiplied by the index of the centralizer G. Remember this number, this index, that's another way of thinking of it is it's the number of cosets of Cxi in G. The number of different cells in the partition of G when you partition it into cosets of this. So you see now we're saying that we're saying P does not divide any of the sides, sorry, not P divides the group, P divides the order of the group, of course. So we're saying P does not divide any of these terms. But you see, P divides the size of G. So if the prime number divides this, but it doesn't divide this part, that means it must divide all the indexes. So therefore, for each I equals 1 to k, it is true that P divides the index of that centralizer in G. Okay? Because P does divide the size of G. So if we're assuming now that it doesn't divide any of those centralizers, doesn't divide the size of any of those centralizers, it means it must always be dividing the index of that centralizer in G. Does that make sense? Yeah. But then we're looking at the class equation, and now we're just using very basic properties of divisibility. We know P divides the left-hand side. P divides the size of G. We know P divides this, divides this, divides this. It divides all of these terms. So the one remaining term is the center. Does P divide that? Yeah, it has to now, because you can write this integer, the size of the center, as a linear, it's the difference between the size of this and all these numbers. So P is dividing this and all of these. It must be the case that P divides that, because we've got this expressed as a linear combination of that and all of these. Okay. And of course, P divides the size of G. So from the class equation, we know P divides the size of the center. And, well, there's a number of things we can do here. We can either appeal to the induction hypothesis. Well, so you might be tempted to say, okay, the center is a smaller group. The center is a subgroup. It's smaller than than G, so therefore the induction hypothesis applies, and the center has a subgroup of size P, and so that's a subgroup of G. There's a slight technical detail you have to be careful of, in that there mightn't be any of these non-trivial orbits, because it could be the case that the center is the whole of G. That happens when the group is abelian itself. Okay, so actually, the class equation for an abelian group is kind of trivial. It just says the size of G is the size of the center, but the size of the center is the whole of G in the case where the group is abelian. So in that case, if G was abelian, then you wouldn't be able to use the induction hypothesis, because this wouldn't have size strictly smaller than N. But whatever, but that's okay, because the center consists of all elements that commute with all elements of G. The center itself is an abelian group. Even if the group G isn't abelian, the center, because it exists of these special elements that commute with everything in the group, so they must commute with each other in the center. So the center itself is an abelian subgroup of G. Okay? But ZG, by definition, is abelian. So actually, we can appeal to that theorem we proved in the earlier chapter 13, the structure of finite abelian groups. Center is abelian. Here's a prime number that divides the size of the center, so therefore the center contains elements of order P, or if you like, contains a subgroup of order P. So ZG contains a subgroup of size P. And hence so does G. So if there's a subgroup inside the center of size P, then that also qualifies as being a subgroup of G itself. So, so that's split into two cases. There was two cases there. The case where P divided the size of one of the stabilizers, and the case where P divided the size of none of the stabilizers, in which case we have to go to the class equation. So in all cases, we proved, so G always has a subgroup of order P. So the theorem is true for groups of size n. So by induction, remember we were performing induction on the size of the group. So we proved now that it's true for size groups of size n, and we had to use the fact that it was also true for groups of size strictly less than n. So we've achieved that induction step. So by the principle of induction, it's true for all finite groups. Obviously, this is something that only applies to finite groups, because we've got a P prime P dividing the size of G. So it's only it's only a concept that's applicable to finite groups. So is that okay? Any questions or queries about that? Okay. So it's a really nice argument. You're seeing a lot of things being used there. Just basic facts from number theory about how divisibility works, and the fact if you've got a load of bits divisible by P, and then you form a linear combination of them, that has to be divisible by P as well, just that basic idea. And then this idea of the group acting on itself through conjugation and the existence of this class equation. By tying together all these things, we get these quite nice results that assert. So the power of this is that it's asserting something about the structure of G, at least one subgroup of size P, based only on knowing the number of elements in G. Okay, so it's quite powerful. It says something. Lagrange's theorem was also powerful, but powerful in a negative way. Lagrange's theorem said you can't have subgroups of these sizes because these sizes do not divide the size of G. It said nothing about the positive existence of subgroups of certain size, whereas this does. Okay, this says even without looking at the nature of G, the nature of what the elements are, the nature of the group operation, just knowing that it's a group of size n allows us to know now that it has a subgroup of size P for every prime P dividing the size of it. Okay, so that's quite a much more positive, strong, assertive result than Lagrange's theorem. Straight away we get this corollary out of it. So a corollary is just a result which just falls out immediately from another theorem, or very often it's just a way of rephrasing the result in an interesting way. And so this doesn't really require a proof because we can see why it's true just by the direct comparison with the results we just proved. So let G be a finite group. Then G is a P group. Now, I need to remind you what that means. G is a P group. What does that mean? A P group is something where every element has order some power of p. Not the same power for every element, but just when you look at all the elements in G, when you look at any element in G, it has a certain, G is a finite group, so every element has finite order. You pick any element from G, you look at its order will turn out to be some power of p. If that's the case, then we call it a p group. It only contains elements of order some power of p. So it's everything in the group has got to do with the prime p. So you call it a p group. But now we can say that G is a p group, and we proved, again, this is a statement, we've already seen this statement for the case of finite abelian groups, but now we're seeing it for all groups, non-abelian groups as well. G is a p group, if and only if the size of G is in fact itself a power of the prime p. Now, why is this immediately obvious given the result we've just proved? So you have to think about, well, how could G not be a power of p? G would not be a power of p. That happens when there's some other prime that divides the size of G. P is the only prime that divides the size of G, and by definition, the size of G must be a power of that prime P. Okay. So this bit could fail to be true when there's some other prime that divides the size of G. But then if there's another prime Q that divides the size of G, the theorem we've just proved says, well, if you've got another prime Q dividing the size of G, G has a subgroup of size Q. Or equivalently, G has elements of order Q. But if it has elements of order Q, or Q is a different prime, then it's certainly not a P group. Because by definition, P group, every element has order some power of that prime P. Okay. So that's the way of seeing why if G, the size of G is not a power of P, then it can't be a P group. Okay. And the if and only if the other direction, well, if it is a P group, no, the other direction, sorry, saying if the size of G is a power of P, then what are the order of its elements? But by Lagrange's theorem, the order of any of the element here, since that generates a subgroup of that order, the order of any element must be a divisor of the size of G. If G is a power of just this prime P, the only divisors it has are other powers of P, other, same size or smaller powers of P. So every element has order of power of P. Okay. So this is a corollary to the theorem we just proved. So I think this afternoon we will, or is that okay on that corollary? Okay. So there's no proof details in the book because it's just falls out immediately by applying the theorem. So let's look at this example 15.3 here. So you can see application of this result. So say to the group A5. So this was one that you were looking at in the coursework. The group A5 has size 60. Prime factorization of 60 is 2 squared by 3 by 5. So now we know, without delving into the more detailed aspects of what A5 is, what its elements are, what the group operation is, just purely by looking at its size, we know A5 must have a subgroup of size 2, a subgroup of size 3, and a subgroup of size 5. Okay. When you delve into the details of A5, you will find subgroups of that size, and you will see they're generated by cyclic permutations of that order. But we now know that just on this higher this higher theoretical level, just by looking at the size. Now the Sylow theorems are results like this. They assert the existence of subgroups of certain sizes, but just more detailed. And they also give information on the number of possible subgroups. Okay. So just in a few minutes, we'll just look at the statements of the results. Not any of the details of the proof or anything, but just look at the statements of the results. And then this afternoon, I think we should at least get the proof of the first one. So the first Sylow theorem is just an extension of Cauchy's result. So Cauchy's result said if the prime P divides the size of G, G is a subgroup of size P. So it's a natural question, well, yeah, but what if G has a factor, not just P itself, but P to the power of 5? So P to the power of 5 divides the size of G. Does it have a subgroup of size P to the 5? Okay. Well, the first Sylow theorem extends Cauchy's result to any power of P. So if G is a finite group, P is a prime such that P to the R, or any integer R, P to the R divides the size of G, then G contains a subgroup of that size, of order P to the R. Okay. Again, you can just tell by glancing at the proof, it's based on the class equation. Okay. Based on the class equation, again, inducting on the size of G, and a little bit of a use of quotient groups as well to step down to a previous case of the induction. So you can use the truth of the theorem for the subgroups of smaller size and then expand it back up using the quotient or the factor group homomorphism as well. That's the first Sylow theorem. There's then a few preparatory lemmas, but we can then look at the second and third. Get them on the same page there. Second and third theorems refer to what are called Sylow P subgroups. So a Sylow P subgroup, so this occurs when you've got a finite group whose size is divisible by P. But what we call a Sylow P subgroup is a subgroup of size, a power of P, but that maximal power of P. So whatever the size of G is, let's say it's got size n, P divides n. Okay, but you look at the highest power of P that divides n. Okay, you look at the exponent of P in the prime factorization of it. So maybe P to the power of 5 divides n. Then a Sylow P subgroup of G is a subgroup of size P to the 5. So it's that maximal P subgroup. That maximal P subgroup. The first Sylow theorem says that they exist. Okay. The second one says, well, okay, if you look at all these different Sylow P subgroups, it actually asserts that they're all conjugate. Meaning, if P1 and P2 are any two such Sylow P subgroups, you can find an element G of the group that when you conjugate the first one by this little G, you get the second. So although there may be multiple Sylow P subgroups, they're all related by this action of conjugation. So that's nice to know. Not only do we assert the existence of at least one subgroup of this certain size, we also describing how all the subgroups of that size are related. They're all related through this nice classic relation of conjugation. Then these ideas culminate in the third Sylow theorem, which kind of bundles the first two up together and adds a little bit more. And what it adds, the bit more that it adds is it doesn't quite tell you exactly how many Sylow P subgroups there are, but it places a restriction. It gives you information about the number, but not the number itself necessarily. Although in a lot of cases, you can examine it a little bit and find out how many of them there are. So same setup: G be a finite group, P be a prime dividing the size of G. We already know that G contains a Sylow P subgroup, a P subgroup of maximal size, of size P to the R, where P to the R is the highest power of P divided by the size of G. Second theorem, we know they're all conjugate. The third theorem adds this, that the number of different Sylow P subgroups that there are, two bits of information about this. So the count of the number of different Sylow P subgroups, it's congruent to one modulo P. It's kind of weird. It's congruent to one modulo P. And also that it divides the size of G. So those are two different bits of information about the count of the number of different Sylow P subgroups that there are. It's quite intriguing. And all of this it doesn't come from examining, the detailed mathematical nature of the elements of the group. It doesn't come from examining the details of the group operation itself. All of it comes just purely from the count of the number of the elements in the group and reasoning about the self-action by conjugation and reasoning based on the class equation. Fairly shortish proof of the third theorem itself. But again, you can see it's talking about orbits and indexes of subgroups as well. So examining similar ideas associated to the action of the group on itself, or related conjugation type operations. Okay, so let's go to just look ahead at the three results. I think we should deal with the proofs of them in like a few more lectures, two or probably two, maybe 3 lectures. And then from that point on, then we'll be ready to dive into going back over everything, but concentrating all the while on exercises. And I want to see, flexing our problem solving and proof finding muscles a lot more. And I'll also release the mock exams for you to have a look at as well, and we can go through solutions of those together. Okay. Okay, so I'll end it there for